All right, welcome to the Process Systems Podcast. I'm Vaughn Watson. Joining me today is Brian Tang and Lewis Solomon. Brian, you want to introduce yourself?
Sure. My name is Brian Tang. I've been working on industrial technology. My company, Shockwave CO2, specifically been working around both shockwave-based technologies using rocket nozzles in the field of mostly pollution control, and then more recently CO2, and then transitioned to water and developing other stuff as well using shockwave-based technologies, but also CO2 capture and recovery, and also liquefaction as well. So kind of branched out to a whole bunch of different categories.
Yeah, so shockwave with rockets. Talk to me about that. That's pretty intense.
So essentially, years ago, one of the founding members of, I'm a second generation inventor working on this technology. The original inventor, dating back to my father's group, had a couple of key developers who worked on a lot of rocket engine technology.
Shout out to your dad.
Yeah, shout out to my dad. During World War II specifically.
Okay.
So developed the jet cone, the modern kind of like airframe and the modern jet cone, and then also rocket propulsion, engine propulsion. So a lot of the know-how was based on the original inventions of those type of nozzles. And then over time, trying to use the principles of this type of technology for other applications. So my father, who was really into pollution control, especially during the Clean Coal Act, original EPA mandate 2007-8, my father worked on that quite a bit, and I helped him quite a bit develop this technology at that time. For PM control, SOx control, NOx control. And that's when we had originally, you might have been on some of those projects with then Peerless.
Mm-hmm.
And then eventually branched out on my own to work on the technology, applying it for CO2. So in all that time, I've been working on both pollution control and CO2 capture using this shockwave-based technology. And then eventually I was contacted by a group that wanted to develop it for water as well. So developed it for water treatment. So kind of the whole gamut of different applications.
Well, that's pretty exciting. I mean, to be able to come up with one method of PM control and pollution control and apply that to multi-processes depending on how it works. You mentioned CO2, and actually I think I need to back up. So the shockwave, is that a nozzle technology?
Yeah, so the shockwave, the basis of the technology is all about nozzle technology.
Okay.
And it's all about using compressed fluids and projecting it out of a nozzle, specific design of nozzle, to create a very specific effect. So in this case, it is expanding compressed fluid. It could be steam, it could be compressed air, it could be compressed other kinds of gases. And it's a very specific type of impingement and release. And when you do release it, it creates a very specific shape. And the shape is called a Prandtl-Glauert shockwave type of, almost like a vortexing tornado, if you will.
Okay, so Prandtl.
Prandtl, Prandtl.
Okay.
Glauert, Glauert.
And that's the shape of the...
That's the shape of the specific shockwave pattern, if you will. So then I do have videos of the pattern specifically, but essentially it's like a spiraling supersonic speed tornado, and it's coming out of the nozzle and it's winding like a big vortex. And in that vortex of release of this compressed fluid, you can do a lot of different applications. So it's got high speed, it's got lots of contact, lots of mixing, lots of turbulence. In the case of pollution control that we were doing originally for the clean coal type of application, you can inject water, you can inject peroxide, you can inject different kinds of caustic bases. And that will, when you have like a a flow of flue gas going through a ductwork, and you basically inject your tornado of compressed fluid in the shock pattern. When you also inject any of these other types of liquid fluids, water, peroxide,
Ammonia.
It could be bleach, it could be a whole bunch of stuff, caustics, it's going to hit the flue gas, and it's going to basically cause tremendous amounts of mixing and turbulence and force a chemical reaction. So then you get really, really high capture rate performance.
So not only is this a mechanical mixing, because of the flow dynamics, but it's also catalyzing the stream.
There's a reaction.
There are a reaction.
Yes. So it's all kind of traditional chemical reaction.
Okay.
So whatever kinds of chemical reaction you're designing for and aiming for, it will do that reaction just at super high speed and also incredibly thorough mixing.
Yeah, I would say this is probably a really efficient way to mix several fluids together.
Absolutely.
Almost like a blender.
That's I call it a high-speed air blender.
Okay,
That's what I
so
call it.
your tornado analogy is probably a good fit for that.
Yeah.
Okay, so but then is the reaction that's taking place due to the kinetics of the injection, or is it due to just the streams mixing?
Both.
Both.
So the kinetics obviously accelerate the reactions. If you are, for example, let's say you're just injecting water, and so I have several examples of where you would just put water on the shockwave. Then what you're going to do is, let's say you're just injecting water on shockwave onto flue gas, for example. When the water touches the flue gas and the shape is coming so fast and it's so high turbulence, high mixing, but high surface area, it's going to contact every single part of that flue gas, especially if you have it in a ductwork where the shape of the expansion covers the entire cross section of the ductwork. So
that's difficult to do though. If you're feeding from like the wall of a duct, how do you pipe it to the annular section of that duct, right?
So that there's a little bit of art to that.
Okay.
And there are different ways to do it. So when we originally did a lot of this demo plants and testing, we did it so that the injection took place down the central axis of the ductwork. So if you can imagine, the duct would, let's say a normal flue gas duct going up, we would come horizontally through our system. It would then come down into a ductwork that we call a shock tube. And then we would design our shockwave patterns to basically cover the entire cross section of those shock tubes, depending on how much flue gas you can divide into many tubes or just the big tube, however you want to do it.
And that becomes your reactor essentially.
Exactly.
Because you're treating it with that cross-sectional spray.
Exactly. So then as the flue gas flows through this pattern, it's going to get hit every single which way, but it's also spiraling at the same time. So it's just creating, contact over hundreds of thousands of times. And then because we're spraying in a liquid, the parts that can condense will fall down as a liquid effluent stream, so as a waste stream. And then the rest of the gas will just keep passing on out the exit duct.
So what temperature is the shockwave being injected at? I mean, is that something that, because of the velocities, gets real hot, or is that like a pressure washer?
The concept is more like a pressure washer. It uses pretty common instrument air.
Okay.
So it's not anything that gets too specific. Anything over, let's say 80, 85 PSI, you can start to form this kind of pattern. And it's just about flow. So let's say if you need, let's call it 100 parts of flue gas or gas that you want to treat, you'd only need to inject about 10 parts as shock fluid or shock air to treat 100 parts of target gas or flue gas or process gas. So the ratio is very...
So it's like 10%.
10%, exactly.
Okay.
It's very economical and you just need regular instrument air. So it doesn't have to be anything special.
So any fluid, I'm assuming, that flows through that nozzle, right?
Yeah.
So it could be used or adapted to any number of process applications.
Absolutely.
So what you originally were a co-inventor, you branched off on your own to grow this company and technology. What is the core market that it was originally designed for, and then what other markets are you trying to serve with it?
So originally it was designed for staged pollution control, and that was a really big deal at the time when you had, especially in heavier flue gases, you had multiple constituents, multiple types of pollutants inside a flue gas stream. So,
and that was that modular reactor,
exactly,
that was covering that boiler feed.
Yes, exactly. So originally the concept was you can convert constituents inside of a flue gas stream into valuable products, but you have to stage each removal
to precipitate out what you're after,
so that you isolate what you really want. Okay, so in this case, for example, let's say you have a heavy flue gas, and let's say it is coal because it was designed for coal. You have your ash and heavy particulates, heavy metals, even rare earths, and you could remove that portion of the flue gas by just spraying in water. And if you needed some sort of additional oxidant, you could use, technically you could use bleach, but you could also use peroxide. You could use a whole bunch of different things.
Any kind of an oxidating base.
Any kind of oxidation effect. And you'll knock down all the heavy parts of that flue gas, okay? And what you're left with is acid gas. And the acid gas can then flow past this module, the first stage, onto the next stage where you're targeting acid gas. So, recently there have been a lot of articles actually posted about coal having a lot of rare earths inside. And we've known that for a while, actually. And my father gave several speeches on it. But coal became unpopular. Everyone switched to gas. But now there's kind of almost like a mini revival on that talk about rare earths within coal and whether that is valuable enough to try to recover or not. But we have a technology that can knock it down from the smoke and have it available to try and recover.
Yeah, that's pretty, I know from being a part of that project, you were eliminating, was it metals, and then your sulfurs, and then your NOx?
Yep.
And then there was a final stage as well.
Yeah, so then if you knock out all the solids, then you're after acid gases, and you can isolate which acid gases you want to target and how you want to go about getting that. But especially in our testing in Poland that we did, so we signed on with a big power generation equipment manufacturer, and we sent one of our test skids out and connected it to one of their coal-fired boilers, and it performed amazingly well. So well that they want to license it and sell it in Europe.
Oh, wow.
So that specific unit, we were targeting SO2, SOx removal, and we injected sodium hydroxide in there, and we were capturing over 99%. So it's like 99 point, even higher than that. But we also captured HCl, HF,
I was gonna say,
a whole bunch of stuff.
Your effluent stream is probably all sorts of stuff, right?
Yeah. So, we broke it down into several categories that we were targeting, and actually our performance was even higher than we had anticipated it to be. So they were very, very pleased with the outcome, and they said, hey, let's go ahead and start distributing the technology. So that was one of the big targets of removal, and that back then was for I forget what Europe was calling best in class, but it was the equivalent of BACT.
Yeah, sure.
Then they had a standard that they were trying to implement for coal-fired power generation at that time. This is before COVID, in 2019. So our tests were throughout 2018, 2019. And while we were at it, they said, hey, can this thing remove NOx? So then we started up a program specifically designed to target NOx. And we were injecting different kinds of chemicals in there, and we were getting some pretty good initial results. So the answer is yes, it absolutely can, and there are different ways to go about how to target NOx using this technology.
And I know you, specific to the shockwave portion of this, you found other applications besides pollution control.
Absolutely.
You and I were having a pretty interesting discussion about water, particularly used reclaimed water or produced water in the oil and gas industry, but even the conversation about dairies in California, where on one side you've got wildfires and the other side you've got a water shortage, and now you're environmentally having to deal with tainted water from rinsing out milk and manure.
Right.
And what do you do with all this shitty milk? You got to do something with it. So what would you suggest an application of this would be for that type of industry?
So it was actually around 2018, 2019. It was originally 2019, I think, that we were approached about developing or turning this technology into a water treatment type of application. Because at the time, there was a lot of talk about what do you do with wastewater, especially out here in Texas, in West Texas.
Mm-hmm.
So there's a lot of wastewater in the oil field. So we started theorizing and designing a water application using this technology. But the main goal of this technology was to use and to take advantage of the fact that you have high mixing, high speed atomization of water and apply heat to it so that you could both, in a way, incinerate the water. You have a lot of constituents in that water that you're trying to get rid of, but you're also trying to drive off a lot of water content, so there'd be less disposal waste. And we had water from West Texas trucked out to us. And as we developed this technology, we started testing a lot on this produced water. It was heavy, it had a lot of salt, had a lot of bacteria in it, had a lot of hydrocarbons in it, and we would run it through our shock blender, our shock air, if you will, and we would both atomize it and then we would roast it with a burner, a natural gas burner, right through the pattern of the spinning cyclone. I call it kind of like a rotisserie, if you will, a high-speed rotisserie, and it would just cook the water extremely clean. So on the bottom, we concentrated the produced water, so it was extremely heavy, and we were able to drive off over 60% of the water content of this water as a big plume, as a clean, essentially like a cloud.
The steam.
Yeah, steam coming right out, exactly. And then we had...
now what about the constituents that were in the plume?
So we had a pretty well-known kind of like stack gas tester, emissions tester come out and measure our constituents in the plume, and it turned out it was exceptionally clean. So so we have the results for that. We kept it. We didn't know what to do with it other than this is, certainly you could call it food grade, but you might not want to, just depending on, because there are certain types of stigma associated with industrial water, but it's certainly industrial grade, very clean water.
Well, I guess there's kind of three elements to this, right? You've got the water that you're trying to A, volumetrically reduce the amount you got, and B, eliminate it or reincarnate it as distilled water. Right. And then two, you've got what was in the water to begin with that's left behind.
Correct.
And then three, you've got the emissions from not only your heat source, but also what got left behind. So can you fill that in for me a little bit?
In terms of
which
one?
Where does I could totally picture a superheated steam stream being very clean.
Yes.
But what about what was in that stream before it was heated in shockwave?
So then you still have a effluent waste stream, a liquid stream, and we basically got rid of all the hydrocarbon content, all the VOC content, and all the bacteria content in there, and we just had a very concentrated almost like a heavy brine that came out of it. And we do have the contents of it going in. It was a lot of calcium, a lot of sodium, a lot of, I think there's some boron. We had a list of the TDS in there, but so we analyzed it afterwards. But we got rid of the sulfur. We got rid of a lot of the acids that were in there as well. So we cleaned off the hydrocarbons, the acids, and the bacteria.
And a big reduction in volume. So
huge reduction. I would say it half the volume on a single pass, more than half the volume on a single pass. And then obviously the more passes you run, the smaller the volume gets, but the less efficient each time, just because you removed so much of the water.
You're now more into that brine.
Exactly.
May not vaporizes readily.
But you know what? Like, so when we were testing all this, and we realized we had so in our mind, we identified we had a super clean heavy brine, and then we had a super clean distilled plume. We started to play around with condensing that plume. So we did buy fin tube heat exchangers, and we were bringing down that plume very successfully. So that was kind of like our add-on module, especially, I don't have a background in oil and gas, but I do have a background in heavy industrials. So my thought was, if we could provide clean industrial water, that would be a huge benefit.
Yeah, it's used as makeup water,
processed water, coolant water. There are a lot of uses for water, especially at refineries and manufacturing facilities, where just having tap water isn't good enough. You need something even cleaner than that. So from our standpoint, we were able to recover that extremely clean distilled water. And at the same time, playing around with ideas, well, what does this brine actually mean? Because in the oil field, you're talking about lots of calcium, lots of sodium. But what if that wasn't the oil field? What if that was a lithium stream? Okay, then we're basically cooking off all the stuff that you don't want, including the water content. And then you have lithium that you're basically concentrating as a lithium carbonate, and that would be pretty wonderful too. So maybe it's a lithium application.
Now, what would you inject in that stream to concentrate lithium? Would it be lithium laced water?
So yeah, when they're digging lithium out of all these lithium formations right now,
they're like panning for gold almost.
Yeah,
right?
They're kind of like big aquifer. They're basically brine.
Okay.
Kind of like oceans underneath the surface. So I'll give you a great example. In the Marcellus Shale in Pennsylvania, they've discovered that when they're mining for natural gas, most of the water coming out of the Marcellus Shale is heavy in lithium. That is actually a very recent and big discovery.
Yeah, they've also found some in like Arkansas, I believe.
So the Arkansas one is called the Smackover, I think. I'm just learning about it just now. I'm not a lithium guy, but there are basically large concentrations of lithium, not as heavy, not as large of a concentration as the Marcellus Shale, but still very significant. So the trick is, how do you get rid of the water content and separate lithium from the water? That's really what it is. How do you separate lithium from water? If you look at traditional lithium refining, especially out in South America, for example, they have these huge ponds that they just let evaporate over the course of years, 3, 4, 5, 6, 7 years. And that's how they drive the water off of the lithium to get to a point where you can
just a retention pond.
Exactly. Right? So that's what they're doing. That's what they do with produced water as well.
Concentration pond.
Yeah, exactly. So like, how do you accelerate concentration?
So agree that it accelerates concentration, and what you're removing is now of a higher purity that can be used elsewhere.
Much higher.
But there's still the problem of you gotta like truck this stuff off for waste incineration. Or
yeah, if you're dealing with like a heavy salt water that is out in the oil field, yes, then you still have to dispose of the heavy brine. So is that heavy brine, is that monetizable? Okay, so that's the first question that people want to know. can I sell it? Can I use it and stuff? So the answer might be yes. And that's something that I've been playing around with.
Okay.
The heavy brine itself has a lot of, depending on which formation, has a lot of sodium, has a lot of calcium. I think it has like a little bit of, what were the other categories? Potassium, has a little bit of magnesium, has a little bit of everything, but mostly calcium and sodium.
Every row on the periodic
table.
Yeah,
it's got a lot of stuff. It's got a lot of stuff. So I told you I've also been working on CO2 capture. Okay, so a lot of this heavy brine, if you put it into an electrolyzer, which I have one here, will turn it into hydroxide. And that hydroxide, if you recall back to when I was talking about pollution control, is what you would inject to target acid gas, such as even CO2. So you can actually use this brine, decompose it with electrical current, and then create your feedstock chemical to capture CO2. And that's something that I've been testing as well. So, it's obviously I'm testing up and down the gamut. I don't just stick with only shockwave based mediums, but I try to think about like the whole chain and what gaps of technology there might be, and then figure out how to develop for that.
Yeah, you're kind of bridging the gap between the technology that you have and where it can be applied.
Exactly.
That's pretty exciting.
Exactly.
So that's one application that you had talked about, and I can see the application with, used water from dairies where you have runoff concerns and fertilizers that contaminate the water, and obviously that can't run off.
Right.
Some of that stuff, reclaiming it may have some monetization capability, but ultimately it's really the convenience of being able to process at least half the volume of it.
Yes. So that's something that was thrown at us pretty recently, is that there is a potential customer that out in Europe, especially was kind of the kickoff one that got us thinking about this. Right now, a lot of dairy plants, when they do their dairy production, their milk, they need to wash out these tanks pretty regularly.
Yeah.
So when they wash out the tanks and they're spraying it down with, water, pressurized water, soap, and all that kind of cleaning product, you have a lot of essentially water that you need to treat. And unless you're a really large facility, you don't have a water treatment plant. So then they actually load up tanker trucks to carry off wastewater on a daily basis. And depending on how large a facility, it could be multiple tanker trucks each day, just full of used cleaning water, essentially is what it was. So you have milk, leftover milk particles in there, you have a lot of soap in there, you got organics in there. So what do you do with all this stuff? And what they were asking is whether or not we can use our water technology to essentially treat their dirty water and then reclaim a large portion of it. Right now, the tanker trucks just take it away, and they don't get that water back, and they have to pay for the tanker trucks to take it away.
Yeah, you've got the fuel cost, you've got the hauling.
Exactly.
You've got basically the makeup water to refill that.
Right. So then
it's pretty expensive, and I could see that being where even if they could cut the haul off rate by half, there's a substantial savings that has ROI.
There is, especially when you factor in that the only two drivers that our technology uses in this particular application is natural gas and gas and compressed air. So it doesn't even use that much compressed air relative to how much water it's treating.
And the natural gas is for the combustion source.
The natural gas is for the heat source.
Okay.
And it's to basically cook off and clean the water as it passes through. So
does it have to be a flame, or can it be turbine exhaust gas, or could it be some off steam process that we can consume as a utility?
It could probably be any heat source, but certainly an intense flame So I call it almost like a water incinerator. And that's very specific because when you do use an intense flame, you cook it clean. So you're getting rid of the pollutant aspects of it and all of the organic aspects of it. So it makes the plume clean, but it also makes the effluent waste stream very clean as well. If you were to substitute that with heat, let's say ambient heat or a co-flow of some sort of heated gas, it wouldn't be as clean. It might still evaporate a large chunk of the water content in there, depending on how high the flow of heat is, but it might not be as clean. I don't know. We haven't tested it yet.
It's just a thought.
Yeah.
I mean, my thought there is, like in a gas turbine, for example, we can inject water to reduce the NOx from the point of combustion, right?
Yeah.
And obviously I wouldn't spray this effluent water into
Right.
the engine, but
Right.
is there, and I guess it would help to understand what temperatures you're looking for. Is that like 1400 Fahrenheit, 1500 Fahrenheit, or higher?
The burner that we're using was measured to be 1800
Okay.
Fahrenheit. So, it's a fairly intense source of heat, and we're basically quenching it immediately by running all these water, the spiraling vortex of water atoms through it.
Mm-hmm.
So, if it wasn't that though, but you could have an equivalent amount of heat, you could probably still do a pretty good job.
Let's you sent me some videos. Let's take a look at these.
Sure.
I mean, talk's cheap, right? We want to see what this thing looks like.
Sure.
I'm trying to do this one-handed in an awkward position here.
Okay.
Which video do you want me to?
So we'll start with this one. This one's good. This is a low flow, and we have it against green light so that you can try to see more clearly. If you go to about midway through the video, you'll see it a little better. So you'll see. So let's see if we can pause it. Okay, this is actually kind of important to explain. When you're watching this pattern, you're actually seeing it cycle pretty quickly. You see how small the little
the
crest around. Yeah. So you're seeing that it's basically undergoing thousands of revolutions. So this is actually a very long pathway for such a short distance. That's very important to note because in the process of water treatment, such as holding under a burner, even though the distance might only be 4 feet or 5 feet or whatever, it's passing through the heat thousands of times to get that kind of heat transfer.
The surface area heat transfer rate.
Super high heat transfer, super high mass transfer if we're doing something else. But you're also going to see that there are black spots. It's almost like a little black hole diamond, and the further out you get, the less you see it, but especially in the beginning. So these are essentially shock diamonds that we're forming. So it is hollow in the middle, but coming back together, just like a helix, like DNA.
Just like you'd see with a rocket booster.
Exactly. So this is the kind of pattern that we're forming. It's very tight spirals, but also kind of folding like a helix on top of each other. And there are hollow points, there are denser points all throughout. And then the runway, in terms of total length, is actually incredibly long, given how small the length of the tube might be. So that's this video, but you see it against the green light. You can see the hollow points inside very clearly.
Yeah, and that's blending the streams because of the collision between the two, right?
Exactly, yes. So then this is in broad daylight. This is with the same class of nozzle, but a different kind of airflow with a much larger liquid flow on top. And you're gonna see all the patterns running on them. You can see running all these spirals going, and then a fine mist of water vapor going out. So this particular nozzle, this particular application was us testing for the water system very, very early on. We were trying to decide which nozzle we're going to use. Every nozzle has a slightly different pattern.
I was wondering why my parking space was clean that day.
But you can see just how tight all the spirals are throughout this shock pattern.
Sure.
And how much water it's carrying. It's actually carrying quite a bit of water. So it's able to project this water as kind of like the spiral pattern. Even though the total distance might be 6 feet, it might be hundreds of feet by time
Sure.
It reaches the end of that 6 feet. So this one has a heavy water flow, and you can see the pattern quite clearly. And this ended up being the nozzle that we selected for the water technology, the water treatment one.
Nice.
So if you go to the next one, this is us using the same nozzle with a heavy water flow spraying onto the pattern, projecting it through a tube. So this would end up being our shock tube equivalent for our water system. You're gonna see how far it can project it through the tube, but it doesn't need to be further. So I want to say this is probably, 5-6 gallons per minute of water for this particular nozzle that we chose. We're using a very specific water spray pattern, so it catches the length of our shock pattern. And then you're seeing that our shock is projecting this water straight down the tube. Even though it's laying horizontally, it's projecting the water pattern about 6 to 8 feet down the tube.
I'm actually surprised how dry the walls are.
Yeah, the walls are very dry.
The
walls are very dry.
I can see some puddle accumulation here, but that's
it's on
probably
the bottom. It's on the bottom.
Yeah.
Yeah. So the top half or top 2/3 of the pipe is very dry, and then you're going to see essentially as the water starts to fall, it'll accumulate towards the bottom, but it leaves the rest of it.
And normally this space would be flowing with heated exhaust gas.
Heated exhaust gas. So in our particular setup, we actually have a burner sitting right here,
Right.
and it projects the flame right through
Okay.
this pattern of atomized water. But if you were to have a high flow of, let's say, heated gas, the whole thing would be flowing through that instead and exchanging with that flow of heat.
Yeah, I mean this is very similar to like our ammonia vaporizer nozzles in the sense that we either do hydraulically atomized or air atomized.
Yes.
But this, you can see it's blending the two streams very rapidly,
Yes.
pretty efficiently.
And always down the central axis as well, which makes it convenient because you don't have too much condensation down the sidewalls either.
That's cool. So essentially, is this the meat and potatoes of the equipment for this, or is
For the
it's more than just a nozzle? I'm assuming we need
Right,
pumps, we need controls,
Yes.
we need valves.
correct. But this is kind of like the secret sauce or the heart of the technology.
Sure.
What makes the initial the kinetics, the mixing, the air blender work in terms of just surface and also contact. And then after that, it's about the art. How do you control your flow? What are you injecting? What's the desired outcome? So those are all things that you design for.
And tailor the control schema to it.
And tailor the whole system. So, in the case of CO2 capture, for example, where we're injecting our caustic in, we needed longer retention time. So then you can add different components in here to have that kind of contact with slightly longer retention. So again, it's an art to
For more residence time.
more
and
residence
mixing
time.
and
Yes,
so forth.
yes.
Well,
So more residence time, you might want, slightly different reaction you might want to control the amount of heat in your reaction, so you'd have a smaller liquid flow, for
Mhm.
example. You might not want air in your mixture. You might want to use compressed, for example, CO2
Or nitrogen.
through the nozzle, or nitrogen,
Sure.
or whatever. So you can actually mix and match based on the desired effect.
That was one thing that kind of fascinated me, going back to the technology where I had worked with your dad. It was like adding the particular ingredient that allowed you to have something saleable at the end,
yeah,
right? And
yeah.
it may knock out a whole bunch of other crap you didn't want
Right.
out of that stream, but then you can selectively precipitate or
Right.
filter off what you did and didn't want
Right.
as a chemical byproduct, as a fertilizer feedstock,
Correct.
as a
Correct.
granular that could be further refined.
Correct. So if you go back to the stuff that my father primarily was working on, he would stage this concept, and the first stage would always be water, because you're trying to knock out all the heavy stuff and then get to the gas, the acid gas that you're looking for, and then you would kind of tailor your injection to make sure that it would ultimately result in the reaction to form the chemical product that you're looking for. So he was always looking for, he wanted to inject potassium. So potassium hydroxide injected in place instead of water, for example, into a SOx stream, which would make potassium sulfate, so a fertilizer. And if you could target potassium with NOx, then you'd end up with potassium nitrate.
Which happens to be very explosive. But
Which happens to be explosive in fireworks,
yep.
but it's also...
Speaking of Chinese New Year,
Exactly.
the Chinese perfected that process
Exactly.
a while ago.
But it also is the main ingredient for Miracle-Gro.
Makes sense, yeah.
So,
Fertilizer.
it really, his concept was, how can you turn flue gas into fertilizer that's extremely high value? And as we keep testing and as we play around with these concepts, the kind of truth that we stumbled on was that even if you could make fertilizer, which we believe we can, and even if you can make all the different chemicals that you're targeting, there's a market to it and a seasonality to this market. So in the end, if you're to have, for example, a flue gas stream that has a whole bunch of different chemicals that you think you want to manufacture high value chemicals out of, you can actually inject the liquid chemical, your capture chemical, and change it up throughout the year to manufacture the actual things that are in demand at that point in time.
Yeah, and then choosing a feedstock that's not more expensive than what you're trying to sell on the back end.
Precisely.
So yeah, you have a clean stream, but when it's costing you a heck of a lot of money for a little bit of return.
Well, so for example, let's say in the growing season, you injected potassium and you came out with and you manufactured all this high-end fertilizer, okay? Then during the winter, you changed it out and started adding sodium, and you're creating all these non-corrosive salts that you can put all over your roads, for example. And when when it starts to melt and it bleeds into the fields, it's actually good for the fields.
It's just like diversifying your chemical capture.
Exactly.
Or maybe even segregating it to where you're getting some of each of these products.
Precisely.
Well, they're doing this now with natural gas, right?
Mm-hmm.
They're taking all these various byproducts out of natural gas, even down to ammonia.
Yep.
And I'm learning my colors: gray ammonia, green ammonia, blue ammonia. Same thing with hydrogen.
There are a lot of colors these days.
Yeah, green hydrogen,
yeah.
blue hydrogen. And it kind of goes back to what are the economics of it?
Absolutely.
Right? Is it the product that you're selling? Is it that your ROI to take care of your environmental or your waste is such a benefit because of its complexity that even if you don't break even, you're still taking care of your mandates?
Yeah. So that's kind of where my father left off, because the technology was proven to have very high performance. And the original application is for power generation. And when you're dealing with power generation, you're talking about massive volumes that would overwhelm any kind of market. And where his head was that if you have these kinds of facilities, these chemical production facilities using shockwave type technology, you would have so much chemical, like what the heck do you do with most of it? And so much of what I've been doing is miniaturizing this technology and turning it more portable. So let's reframe the question. Let's say instead of trying to address 100% of the pollution coming out of a flue gas stack, we only try to manufacture what the immediate market wants to use. And if you only scrub 10% of that stream, because you can only sell that much product, then that's how much you would actually target and scrub to make your product. So you don't have to treat 100% of the stream. So it's not necessarily a pollution control type of
Yeah, but I mean,
mentality. It's more like a chemical manufacturing type of mentality.
agreed. Title V might disagree because if you have I'm trying to think of an application. Let's say you had a dairy in California.
Yeah.
Right? Water's crazy expensive as a resource, as a utility out there. Your environmental permitting is such a high burden for a lot of these facilities. In fact, we saw that P66 had talked about backing out of some of the refineries in Southern California for these reasons. Governor Newsom's new policies had driven them to a point of, hey, I'm really breaking even by the time I do all this. This plant's old as can be.
Yeah.
I may just divest out of it because of these things. But a small mom and pop farm, the burden to treat all of their waste is so expensive. And so, like you said, miniaturizing or right-sizing it to their process size, application flows, whatever, it is pretty essential.
That's basically the crux of my mindset for the past, at least 6, 7, 8 years, which is taking this very, very impressive concept that he was developing, always at a large scale. When you're talking power generation, it's just large and larger. And thinking, instead of trying to do that, how can we make it smaller and smaller and more practical to the market? So every iteration of technology I developed has been smaller and more portable.
Yeah, I mean, I was joking about the parking space earlier, but the entire scope of your test apparatus fits in a parking space out back. So from a real estate perspective, it's not like you need all this acreage to put a treatment plant to deal with a water waste stream, or maybe several effluent waste streams from various things.
It's pretty small but pretty powerful, and it does a great job with what it is. And if you wanted to treat more stream, you just get more of them. That's my concept of being portable and modular.
So one of the big issues that I've been seeing a lot of is on this renewable natural gas, where they're taking landfill gas or digester gas and blending it with natural gas streams, because it's it's some elimination of carbon, but you're really utilizing a biogas, right? Well, the problem is you've got siloxanes as a constituent within these fuel streams, and the turbine guys, they say, hey, you scrub it to X amount of microns, we're okay, the blades will survive, etc. What they don't tell you is, you may get it through a scrubber to not kill your turbine blades, but it's going to wreck in seconds the SCR catalyst. Siloxanes are like a top offender of poisons on an SCR catalyst. And we've been seeing plants that, other than checking their gas chromatograph, they didn't know they were getting streams of blended fuels because it's being blended into the gas pipelines at X percentages, and even parts per billion of siloxanes are going to harm an SCR catalyst.
Well, parts per billion is going to be tough to scrub. And I'm not going to say impossible, but very difficult. So what I would say is that if you had a gas stream that had what you're talking about, different kinds of pollutants in, that's basically what our original design was for, to scrub down to a micronic level these gas streams. So that's why, like I said, when you see the pattern, it's contacting the gas thousands of times and trying to condense out whatever it can condense out. We're trying to react out whatever it can react out. And so when we used this scrubber, we did a test in Poland, we did a test in China, pretty big plant in China actually, and its performance was exceptionally high. So higher than your average sulfur scrubber, your average scrubber, much, much higher. I want to say the 99% plus category, almost across the board. So it has very high performance. Now, whether it can do parts per billion out of siloxane, that's more specific, but it's something worth testing for.
Yeah, I mean, I think the issue is coming about more and more because of this fuel blending.
Yes.
It's just like I was at the American Boiler Manufacturers Association meeting last weekend, and they talked about hydrogen blending.
Yeah.
And what you are dealing with right now is that all the burner companies and all the gas turbine and the engine folks are saying, yeah, up to about 20 to 30% blend,
Mm-hmm.
don't worry about it,
Mm-hmm.
all good. The existing technology can accommodate. As we move out further from those 20 to 30% blends, there's a lot of stuff that takes place in the combustion, and the NOx levels rise and the temperatures are different and all these other things.
It's much hotter. Yeah.
It gets much hotter.
Yeah.
And so now you're dealing with a new set of problems in a world of decarbonization
Yep.
efforts that are becoming more and more prevalent.
Mm-hmm. So I would say that as the uses keep changing, the technology has to keep changing. And that's one of kind of like the mission statements of my company, the modus operandi, if you will, is that if you've seen how many times I've changed the shockwave base, the heart of the technology, that's kind of like a consistent evolution that will always take place. We're talking about heavy particulate control, fly ash and that kind of stuff, to SOx, to NOx, to CO2, now to water. Recently, you and I were talking about a different type of NOx application,
Mm-hmm.
which would be something that we actually theorized this maybe in 2017, but never acted on, which was this shock lance direct injection type of application for NOx. So getting rid of the APCU, getting rid of all these different other potentially less efficient ways of atomizing or vaporizing, and just to inject a low flow of ammonia, for example,
Mm-hmm.
directly onto our shock, and then mixing that into the ductwork. So you can bypass potentially a lot of equipment and make it significantly better value, and smaller equipment to do a better job.
Yeah, and there's a lot of applications to where this really comes in clutch, right?
Yeah.
Yep. Tall vertical fired heaters.
Yep.
That makes total sense.
Yep.
Your simple cycle gas turbines, particularly where you don't have a CO catalyst, where you either have SCR only or a multi-pollutant
Yes.
catalyst,
Yes.
where the oxidative portion happens after.
Mm.
But essentially arranging a number of these shockwave nozzles at the wall of the exhaust duct to
Yep.
inject and penetrate into the exhaust gas stream. And then it goes back to what we were kind of joking about, of he who wields the
Right.
greater CFD wins.
Right.
Is, can you model the shock diamonds and what effects that does for blending a reagent for NOx control into a stream of exhaust, and have enough mixing
Yeah.
effect?
I think the answer is going to be absolutely yes.
Sure.
I mean, even by the videos that you saw about how the pressure basically projects and can overcome a lot of gravity and all that kind of stuff. It projects with force the liquid, and it delivers it to the destination. So in that particular application, it's all about the art of design and what kinds of angles and how far do you want to penetrate into
Mm-hmm.
the flue gas or whatever it is. So yes, absolutely. I think that will be sooner than later.
Well, that's good. I think there's a lot of applications to where, best available control technology, but also best available retrofit control technology,
Mhm.
like you're seeing out in California.
Yep.
Where, hey, that's great that you had what was fashionable in the 90s, early 2000s during that era of deregulation. Now it's looking like you're going to have to upgrade X amount of units above a certain megawatt rating
Yeah.
to achieve these new retrofit control technology applications or milestones.
Yep.
So
Yep. So I think that so much of it is just the ability to, if you understand what you're working with and you have a deep passion for development, which I happen to, you've seen me work here for quite some time.
Yeah,
developing.
What you lack as a friendly feedback is the go-to-market on it.
Yes.
Right.
Yes,
I
yes.
think what, and this is inherent with a inventor.
Yes.
Is you want to, let me go do R&D.
Yeah.
Instead of saying,
yeah.
let me put forth a sales force to turn this into a revenue opportunity.
That's pretty much the weakest part of everything that I've been doing, is that I'm so enamored and fascinated by the technical aspect of overcoming and problem solving that I haven't really placed as much attention on the commercialization aspect of it, which I need to. And so from so much of the development that I've done, whether it's pollution control all the way to, I know I've tangentially, I'm in liquefaction now.
Okay.
Because people were always asking me about CO2 capture, and it ends up being that they have a lot of processed CO2 that they want to capture, specifically in this case, even at manufacturing plants. So, I went out of my way to develop a portable liquefaction system, CO2 liquefaction, and the kind of funny, they said that they had a blended CO2 gas, because there's a lot of air, there's a lot of ambient air in the CO2 gas. So I had to develop, kind of a CO2 air separation device that would liquefy while it purged the incondensable air. So it's like I'm so heavy into development and not heavy enough into commercialization. So the path that I took for this particular project was I found a partner who is very knowledgeable about the CO2 industry. They distribute a lot of CO2. And so I'm working with them to help me commercialize the technology. But I myself am not as commercially minded as I am kind of development minded, I should say.
Yeah, and I think that's where it helps that we have a shop. Right? Vector Systems is really good at process improvement and process applications.
Yeah.
I don't have a shock technology. I don't have a secret nozzle.
Yeah.
But what I do have is the ability to package all this stuff into a ever decreasing envelope size, but then tailoring that custom to each individual application.
Right.
And we also have a lot of background experience with the controls.
Yes.
And the programming, but also the flow and measurement that is essential to this thing working.
Right.
So I think we can help a bit there, but also, we're into different markets, and it seems like in 2025, I feel like we need to be in exponentially more markets than we're in right now.
Yeah, and I would say, and that's, so my company is called Shockwave CO2. I really spent a lot of time developing CO2 and CO2 related applications. And so much of what you say hits the nail on the head, is that you have to chase where the market is and where it's going. And when I was developing CO2, you have to recall this is like 2007, 8, 9, 10, 11, 12. People wanted CO2. There was a hot topic of, they call it anthropogenic or post-combustion CO2, that they wanted to reuse, called CCUS, carbon capture utilization and storage. So I was developing all this stuff for CO2, but then as time went on, CO2 kind of came and went. People don't really talk about reusing captured CO2. Now they're talking about burying CO2, which is different. So that's CCS, carbon capture sequestration.
Mm-hmm.
And so I've been developing what is my primary interest and what was my mission statement, but the market keeps shifting, and you have to chase what the market wants and what the market will want, which is also how I got into water and liquefaction and other stuff, because developing technology that was solely focused on post-combustion CO2, over time it's hot or cold. And if you're in the cold cycle, you're just kind of out of luck and you have to do something else. So I've been trying to spread and diversify all the different things that I've been working on, just so that I have more technology offerings depending on which cycle you're in.
Yeah, that makes total sense. I mean, right now it's drill baby drill.
Yeah,
I mean, we're expecting a kind of a renaissance.
Yeah.
West Texas oil and gas.
Well, for the last 4 years, CO2, the mention of CO2 pretty much went dead. Okay, so post-combustion CO2 was out of vogue. They didn't want to capture CO2. They wanted to bury CO2.
Sure.
So the only thing you ever heard about was, can they analyze a site to inject CO2 from some process and just bury it and forget about it?
Mm-hmm.
And only a couple of companies ever did that, okay? Because everyone else couldn't get the permit or whatever it was. And so the only other mention of CO2 for the past 4 years is about direct air capture. So they want to put all these fans and blowers on top of mountains or whatever and suck ambient air and drip some chemical in, and hopefully you can capture air out of 4 ppm at a time. So that was where the policy and the market was, government funded market, and CO2 post combustion wasn't a thing. So that's why I had to go into process CO2 and all this other stuff. But now that there's drill baby drill, people are going to say, hey, look, if we have a lot of opportunity, and if we have CO2 source, for example, then we might want to think about injecting CO2 into floods, into frack, into all that kind of stuff. And now it will be a valuable commodity again.
It's back to being a very readily available utility.
It could be. So we're all kind of waiting to see how it unfolds, because it's only end of January right now, but CO2 could be back on the menu.
Well, I completely relate to what you were saying about, is it in vogue or not?
Right.
Because the EV crisis.
Oh yeah.
I say crisis.
Yeah.
As a car guy, I say crisis.
Mm-hmm.
As a person that drives a V8 every day.
Yeah.
And you were talking about lithium earlier.
Yeah.
The demand for lithium has gotten real quiet recently.
It has.
There's been a complete redirection of resources at
Yep.
all the big three and the Asian manufacturers for vehicles. I think you've got a lot more investment becoming the hot topic on data centers.
Yep.
And advanced technologies. There's a term, and I may screw this up, I'll fact check it later, but hypermotivators.
Okay.
These are companies like Oracle, like Amazon, AWS, like Apple, that are out there pushing these advanced technologies for AI and crypto and so forth. And that these folks are going to be the ones that are going to have to generate their own power because of the amount of need for it.
Right. Bypassing the grid, by the way.
Yeah. So
that's like another topic.
we could spend another 2 hours
Yeah.
talking microgrids.
Yeah.
Because I'm really into that too.
Yeah.
I love that concept.
Yeah.
That's what our defense strategies are made up of.
Mm-hmm.
But also you've got these individual power islands housed locally.
Yep.
Right. So they can't be done in a very urban environment, but it can be done out in West Texas.
Absolutely.
Or Western PA or
Absolutely.
Ohio.
Absolutely.
And they have enough acreage that they put in a few gas turbines, and they're recovering the heat that's generated from the server processing. And we've done studies to where we can recover and circulate those with pumps and chillers to aid those processes. But you're talking about lithium ion is out because of EV batteries. Now it's all in on AI. But then I saw this morning people were worried about hacking of AI because of the Chinese technology that just came out. Deep
think or deep something.
It
gets deeper and deeper. Yeah. So let me backtrack a little bit and see if you can follow my thought process, which is how I developed. I developed trying to create a full circular economy, but like a full loop of technology. Okay. So imagine data centers being installed in Abilene. All right. Halfway between where we are, DFW, and West Texas. Okay.
Mm-hmm.
So then they need gas from West Texas,
Mm-hmm.
and when you drill, you have produced water. Okay, this produced water, if you run it through my water system, for example, you drive off most of the water content that you can condense as clean water as cooling water for your data centers. Okay, then the brine content, which is heavy salt, heavy brine, you run through the electrolyzer that I've been developing, and then you come up with your hydroxide. Okay, this hydroxide can be sprayed down the central axis of these, single cycle or combined cycle gas power plants, and you're actually capturing the CO2 out of it. So then you have a much cleaner gas with less CO2 emission, if that's your priority, but you also have the water content, the clean water, the distilled water that you can use as cooling water for your data center. That's actually could be a pretty big deal.
I would think so too. I mean, we are looking at right now 2 20,000-gallon stainless steel storage tanks for aqueous ammonia going to the facility out in Abilene for that data center. So we're covering the emissions controls on the gas turbines. The next phase of that is to do the fuel gas conditioning for that 4 gas turbine microgrid that they're developing for their own data center, Project Stargate. And okay, so we got the emissions controls covered for that. We got to clean up the gas. That gas came from the well that has a produce water concern. We've got to look at things like removing and separating out black powder as a constituent in this gas. We've got to also look at the cooling, like you mentioned. We need water for cooling systems. So Vector's been trying to evaluate the chillers and the exchangers and the pump skids for circulating and cooling those servers. But yeah, like you said, there's a whole life cycle at each of these facilities that can benefit.
Absolutely. So I do think that, it was actually by design that I've been working on these specific technologies. The whole point was to link them all together, but develop one at a time. And that's what I've been working on and focused on. Probably should focus a little bit more on commercial activity, but all my attention was on developing so that I could close the gap and close the loop on these different technologies.
Well, good. I think it just is a matter of finding the use cases.
Absolutely.
Customers that are faced with a problem, whether it's muddy milk or water in their well that they need to treat or so forth,
or they need industrial water, or
I think finding those use cases and then tailoring that package to include the piping, the valves, the pumps, the compressor for the plant air or whatever is needed into a package that is skid mounted or modular or mobilized or trailer mounted, whatever that needs to be.
And just a brief segue, we were talking about lithium, how it's kind of out of vogue now. Lithium is one of the most reactive chemicals to capturing CO2. So if we were to, for example, have data plants in Pennsylvania and they're using all the gas out of the Marcellus, you take that lithium, you cook it with my water system, you get a lithium carbonate, you pop that into the electrolyzer that I've been developing, you get lithium hydroxide. That is the CO2 capture that they use on board spaceships. They use lithium. So then you have very reactive chemical capturing all the CO2 out of these gas plants if you want. And if you want CO2 supply, then again, you take the lithium carbonate, you pop in the electrolyzer, it actually frees up and decomposes and creates a CO2 stream that you pop into my liquefaction unit, which is designed to liquefy CO2 while it purges incondensables. So I can even bring the CO2 down as a commercial stream.
Interesting. So you've got, okay, so walk me through this here.
Sure.
You've got concentration. Then you've got
concentration and water recovery. So those two different.
Yeah, concentration, water recovery. Then you've got.
Then I've got the electrolyzer. So you take the concentration, you put it through the electrolyzer. The electrolyzer, what it does is it takes the concentration and it splits it. Okay. On one side, it'll split it into caustic hydroxide. On the other side, it'll free up CO2. Okay, CO2 sometimes with oxygen. Okay, so the CO2 splits up as a gas stream, and I can use that on my liquefaction technology to recover that CO2 as liquid CO2. And the rest will pass through with O2, so you have an oxygen stream. Okay, on the hydroxide side, you do have hydrogen given off, but you also have your concentrated hydroxide, which is the capture chemical that we would use to capture CO2.
Wow. So like you said, it's all interrelated and modularized.
Yep. From the very get-go, it was kind of like, how do I map this whole thing so that it could work out in unison and then develop them one at a time.
And right now you have something that now just is a hammer looking for a nail at this point, basically.
I have, so individually, each piece of technology stands on its own. They have a lot of different applications and hopefully ways of monetization, but they can also be worked together for, you know, kind of like a full circle of technologies.
And they can be mounted on one piece of equipment if needed.
Correct.
Wow. All right, well, good. Well, let's wrap this up. Brian, thank you for sharing this. I thought the videos were cool. I'll be interested to see when we can start kind of sizing up some of these for need case applications.
Yeah, definitely.
I know myself and Lewis are excited to support the Shockwave team.
Thank you, Lewis.
So, good. Well, let's wrap it up.
Awesome,
Thanks for your
man.
time.
Thank you. Thank you, Lewis.
Thank you.